explaining the sockets with applications and how does a socket act as a door towards before I start, coursework, any progress? Nothing? Any questions till now? Okay, I still have 3 months left, so still time. So just don't leave it late, guys. If you have anything, just pop in. Just show me if you have anything regarding the programming or even the normal research work. Try to help as much as I can, okay? I've already delivered the exam questions, so roughly I know what's happening with the exam, so try to focus mainly on the exam parts. Okay, so before we start, remind me, what is TransportLayer? Where does it reside, TransportLayer? Remind me, where is it? So if I would say TransportLayer, where is that? Number 2, 3, 4. So mainly TransportLayer resides below your application layer and above your network layer. So here will be your TransportLayer mainly. So what does the TransportLayer do? What does the TransportLayer provide? Anyway. So network layer mainly deals with end-to-end devices. So we are dealing with packets to be delivered within end-to-end devices in the network layer. So if I say TransportLayer, what does that provide? So what is it? Instead of having the end-to-end device, what is it exactly? So mainly TransportLayer is what we call a logical communication between an end-to-end device. So the word logical communication, what do you think that is? A logical communication. Everything is depending on sequence of steps, but I mean the word logical and physical. So why do I need the word logical now?
Because it's nothing to do with the actual physical devices.
Exactly. I'm dealing with a peripheral network. I'm dealing with the edge of the network. I'm not dealing with the core. So if I would say 2 connections, that's A as a PC or a host connected to B. Usually that will go through a number of routers until it reaches the destination. On the network layer, or even the lower layers, deal with that part, with the routers itself. But within the actual application and within the actual process, there's no actual physical devices. Mainly you are dealing with the process within your application layer. So that's your logical communication. Mainly dealing with the process, the logical part, rather than the hardware. So mainly that's the logical part, the communication of the actual connection. So if I see here, the logical communication will be mainly dealing with those 2 layers, direct communication between the processes of the application. If I were to try each one of those hosts, we'll be looking towards the network as an end-to-end device. The actual, if you are a user within the transport layer, you don't care what's happening, including the network layer. You don't care how many routers you're passing on. You don't care whether your destination is in the next room, in the next platform, in the next continent. You don't care. The main thing is you're trying to deliver the right process to the right application. What happens when the message goes by from the higher layers to the lower layer? So if I'm trying to deliver a message from an actual application, that will be a message passed on to as a lower layer. That will be breaking into what we call a segment. A segment is, as you might already know that now, a segment is a part of the message added to it the header of the transport layer, creating your segment in the end. What kind of protocols that carry that process is your TCP and UDP. I think most of us know TCP because we associate the internet with an IP, TCP IP. And we are going today to explain exactly each service within your TCP, each service within your UDP, the differences, what kind of services can be provided as well with each one of those. So if I would say TCP, what's that? That's somewhere to create a connection. But no, if I would say TCP, first of all, what does a TCP acronym mean? Transmission Control Protocol. The first one with TCP, the first thing that comes to my mind is a reliable connection. As we insisted during the first lectures that To provide a reliability, you need to add a sliding window protocol over a specific time of unreliable parts of protocols. Like point-to-point protocol, we add sliding window protocol to provide that reliability. With TCP, it's a reliable connection. Meanwhile, if I say UDP, what's that? That's the user datagram part, which is reliable or unreliable. What do you think? That's an unreliable connection, mainly. So, if I would say now a TCP a reliable, what does a reliable mean? The word reliable is very general. What do I mean by reliability? So what does that, if I'm delivering a packet, or a number of packets from the source or as a destination, what do I need them to be, in what to be reliable? You need to be in sequence in order, they are arriving from A to B, they need to be in order, 1, 2, 3, and so on. You put them into an order. That's reliability. What else? That's one.
All of them have to reach the destination.
All of them to reach the destination. So in other words, you need to receive all of them without any issues. In other words, you need to have as an acknowledgement saying that I've received all your 3 packets. What else? Reliability.
It have to be in the right order.
Sorry?
You have to be in the right order.
That's an order that I already said that. That's a sequence number related to your order. They should arrive without any loss of packets. As you said, they all need to be arriving. What else? What's missing? Sorry?
Confirmation.
Confirmation is in the acknowledgement. So that will be part of the reliable where you acknowledge receiving the packet. That's part of the reliability as well. Did you miss anything? What? No, nothing to do with the speed. If you deliver a packet in 1 second or 2 seconds, it does not affect the reliability, it just affects the speed. When I say reliable, I can add to that. Rather than having that only in order, they shouldn't be duplicates. So I don't want to receive number 1 twice. That will be part of it as well. Okay? No missing segment, that's a part as well, when you said need and having all of them at the same time. To do that, I need to have some sort of services. The 3 services that I'm going to use are condition control, flow control, connection setup. When you mention the 3-way handshake, that's mainly a connection, and I'll explain exactly what's that. And that's what we call a connection-oriented one. But I'll explain that in full details later on. When I say unreliable then, what do I mean? How do I provide unreliability? Okay, we said unreliable. We said reliable is providing this in sequence, in order, without any missing, without duplicates. What's unreliable then?
Fast.
It's fast, but again, what do I mean by unreliable? It's the opposite. I don't care about the order. I don't care if there's duplicates. I don't care if you already received any of the packets. I just send them. I do the best effort. That's what I call best effort connection. Exactly, that's the internet. That's the best effort connection. I don't care. Mainly, I just want to deliver the packets. I send them. I don't worry about that anymore. Other people will deal with it. But other people, I mean other protocols. So if I'm a UDP protocol, I'll just send the packet. My only duty is to forward the packets towards the destination. Higher layer or lower layer, i.e. the sender or the receiver. Okay? That's mainly what UDP is. And we'll explain that in full details, what do we mean in the services part. So it's a no-frills one. It's an extension of a best efforts IP. Because IP is unreliable as well. How do I provide reliability? Go back to sliding window protocol. So if I were to provide a reliable service over a protocol that's not reliable, just put sliding window protocol, like point-to-point, that we did in layer 2. That's layer 2, that's an unreliable service. We added point-to-point, and we added sliding window protocol over point-to-points to provide reliability. Service is not available. It can be delays. It can be bandwidth issues. I'll deal with that in the later stages. That how can the delay be affected by providing a reliable service or an unreliable service, or how can bandwidth be affected by those services. So each one of them will have advantages and disadvantages. Okay? So, we mentioned in the last lecture the sockets. So I wanted to give you an example. How will sockets play an important role within the process from the higher layers to the lower layers? What is a socket here and how can a socket be acting within those APIs? So before I go further, the services in the application layer protocol will view the network as a peripheral. As I said, the actual applications will only consider delivering the package to the right application in the destination process. So if I would say here, the transport layer is sending a packet, the only duty is to arrive to the right process. So if this is an HTTP protocol with your application layer, you are sending it as a process towards the destination. I don't care whatever it is in the core of the network. That's how the application operates. It's acting as an end-to-end communication to reach the destination, to arrive to the transport layer, so the transport layer can deliver it to the same HTTP application in the destination. In other words, you are downloading a file within any web service application. You try to download a picture. So whenever you request that download, it's basically a process being sent towards the same process in the destination to reach the right application. That's it. So this is how it works. That's why the word logical here is being mentioned heavily. So there is no relation to the core of the network within your transport layer. Mainly you're dealing with the process and the applications logically. That's it. These are carried simply by, again, TCP and UDP. TCP basically is a reliable service, and we'll add a sliding window and how can we have the reliability with the both and error recovery strategies. That's your go backend and your select route. With UDP, it's basically just delivering to the right place. The communication is achieved via the socket abstraction. I think in the last lecture we explained in details how the socket operates, the addressing of sockets, and how can you program a socket. Just to remind you, basically, if I would say I'm trying to send a process through an application, so if I would say now, this is a host as a client trying to communicate to a server. Let's call it host 2. So basically, it's the process from the higher layer. So this is your transport layer. So let's say you're an application. You're trying to send information. You're using an FTP protocol. You're trying to use an FTP transfer protocol as your application layer. So you're trying to upload files. How would that operate? The actual application will send the process towards the transport layer. Again, transport layer needs what? Needs an interface. What's your interface in here? Okay. Sorry?
Socket.
The socket. That's exactly what's your interface. So basically, for the actual application to communicate to this layer, it requires sockets. That's basically what it is. So the socket is acting like a door, like an access door between your higher layer, the application, and the lower layers. That's it. You might have more than one socket. So for example, you might have, you are working on a PC as a Windows operating system. You try to download a file using an HTTP. That's a process. At the same time, you're uploading a file using an FTP protocol. So how many sockets are you using? You're using 2 sockets because you have 2 processes. That's exactly what it is. You have an HTTP, and you have a file transfer protocol, for example. Each one of them will have its own socket inside that transport layer. Each one of them will be activated by the application whenever the application is. So do you understand now the socket, how it's operating? How it's actually controlling your layer? So that's basically what it is. That's basically what the socket is. How would that socket be? What that socket can be? What kind of protocol that socket can be? Can be either a TCP or UDP. That's basically what it is. Any questions? Before I go further within the actual transport layer, within the TCP and UDP, I want to make a small comparison between layer 2 and layer 4. In reality, both of them are very similar. both of them have the same process applications to deal with the same principles and laws of each one of those layers. Transport layer superficially shares many similar communication problems with layer 2. And thus, you have your actual sliding window protocol for both of the layers. But that's dealing with the higher, you're dealing with application processes, that's dealing with the network layer. When a reliable transport layer service is required, the environment makes a solution but will be more complicated. So transport layer will be more complicated because I'm going to deal with now selective repeat rather than just go back in. In here, in layer 2, not layer 4, in layer 2, I'm dealing with point-to-point protocol. So when I say point-to-point, I mean that two end devices, like this time will be routers, because I'm dealing with the physical part, the data link layer, that will be your point-to-point. Those are connected to a connection. So only one sender and only one receiver. With your transport layer is the same. Rather than having it in the routers, you'll have it in the process. So it's an end-to-end, but with a process communication, rather than the router. And again, it's a single point-to-point, a one sender and a one receiver. So the word multicast, i.e. sending from one user to multiple, is not working. Basically, it's just a point-to-point connection. But with the layer 2, it's between the routers, between layer 4, it's between the processes. That's it. These are very similar. And therefore, for me to arrive with a reliable service, both of them require sliding window protocol. Okay? That's basically when I mentioned that how an actual socket is operating. A socket will be created based on the application process. So from the higher layer, if I look on the leftmost side, as a sender at the moment, in here your socket is being a TCP. That socket, whenever you have a process trying to send the messages, i.e. as a processes, to be sent to as a destination, a buffer will be created. That buffer will store, remember I said you have a descriptor. That descriptor will be having an identifier. That identifier is related to your actual protocol. And that will create an actual buffer inside that layer. And that buffer will control sending and receiving those information. Basically, that's what it is. Okay? I'm trying to break down the transport service itself to try to make it easy to understand what does transport layer do. Okay? That's really what I'm trying to do today. As I said, layer 4 environment is an end-to-end. Across a network or set of interconnected networks. It might be a LAN, it might be a wide area network. It doesn't provide reliable service like the internet unless I use TCP. If I'm using UDP, it's basically just an unreliable service. So transport layer protocol must be able to provide, if requested, a reliable full doublet separation. It can be done between two any processes, or any kind of process that is. It can be situated anywhere in any set of interconnected networks. It might be the internet, the phone, whatever that is, or it might be a local area network. Potential problems with the transport layer are three main problems. One, addressing. I'm going to explain addressing. We explain a little bit about sockets and how can port number and IP addressing be together to create a socket address, i.e. transport layer address. We'll explain a little bit about error detection and correction, right, in the recovery, how that's happening. And I'll explain more in details of flow control. Okay? Addressing is how you identify multiple processes on any machine despite the multiple intervening sockets. So i.e. how do I associate the port numbers with your IP addresses? Error detection and recovery, regardless of the network limitations, whether that's a reliable or unreliable, I need to explain about how can a reliable server operate and how can an unreliable detect errors. Flow control, how to allocate a buffer space with multiple conversations and conversions on the same host. Problems with the end-to-end environment means when you have an end-to-end environment, that creates a large, huge network. So when I say huge network, that means you have an end-to-end communication, an end-to-end connection. That will create a delay. So if I'm trying to send information across the network, usually delay occurs. And what kind of delay that will be? One of the delays that can be propagation delay. Can you remember what's a propagation delay? a conflict whenever you are using what you call medium multiple access control protocol. That's you are allowed to send, but you couldn't listen that the other side is sending at the same time. No, that's not exactly what it is. Propagation delay. Yeah? So it's the matter of, if I would say formula, what do you think it is? It's the distance.
Plus,
No plus.
divided
By speed, exactly. That's it. So that's the propagation delay. So that's for the packet to arrive from the source to as a destination. Depends on the distance and the speed. So and with your large networks, you'll have issues. Okay? So that will create more issues within delivering to a right destination. What else you will suffer? You will have what we call bandwidth and delay will be related to each other. So people might say, okay, why don't we just increase the bandwidth? Will that not decrease the delay? What do you think? If I say you have 1 meg, okay, and you try to deliver packets to as a destination. If I increase it to 2 meg, will that affect the delay? Why and how? And is there any other factors? What do you think? So you have a connection of 1 megabit per second. You're trying to arrive from point A to point B. If I say that's creating delay, and I say, okay, use 2 megabit instead, would that solve it? And would that is only related to the bandwidth? Or is there any other factors affecting it? What do you think? So first, if I increase the bandwidth, will that help? Will help. Why?
And because you come with, it depends about how many people are using at the same time.
So there are other factors.
Yeah.
When you said other people, that means how heavy this connection is being loaded by other people. You might have another issue. You might have, one of those controls is actually flow controlling it. So TCP, what does TCP do mainly? It's control the condition. In a sense, it says that if I have 2 connections with a router in the middle, rather than heavily giving it full access of speed towards the router, then eventually that router will be dealing with heavy traffic. I control the traffic. So in other words, you might have still 2 megabits, I'm sending in 1 megabit per second, because I don't want the router to actually drop. I don't want the router to drop because he cannot process the speed of the sending of information, if you remember that. That's what we call a condition control. So in other words, increasing the bandwidth alone wouldn't affect the delay mainly, because there are other factors affecting it. So therefore, I want to know exactly what are the factors that affect sending and making that delay to reduce the sending time and increase it. And explains what's called condition control by the TCP as well. So that's when I add reliability on the network. When I try to add reliability, other issues will occur. It will occur delay. You'll have some other issues that I will discuss in details. If I have unreliable service, you still have problems. Yes, you will have the speed. Yes, you will have less effort. You don't care about the actual packets. But you'll have the main issue of not controlling the network. Because you cannot control everything. Because you don't have that sort of condition control or flow control or any other reliable characteristics to control the actual band and actual speed of the network. So network layer can discard or delay packets because there is no reliability. If you can drop the packets, if there is no acknowledgement, no one will receive that, you receive that packet or not. You'll have issues with an unreliable service. TCP might time out with the issues of a duplicate. If you have a duplicate without your reliability, then that's an issue. If you receive the same packet, you don't know which packet it is. You remember when we said you have a sequence number, and if you receive number 1 twice, it might be a new or an old one depending on the situation, so that might be a duplicate. How can we solve that issue as well? Otherwise, there will be 2 copies of the packet, and then an issue will be up. Okay? Let's go into now UDP and TCP in details. And now it will be a little bit easier to track exactly what we said at the beginning of the 24 slides. So UDP is basically a no-frills. It's an actual bare-bones network. It's an easy part of sending a message from the source to as a destination in that sense. So basically, no reliability whatsoever on that protocol. It's what we call a best effort sense, where the segments can be lost, they can deliver out of order, they might be duplicate as well. So no sort of control. There's no connection oriented, it's a connectionless. So what does the word connectionless mean? I need you to give an attention to this one. What does a connection oriented or connectionless mean? So if I would say UDP is a connectionless, what do you think that is? You mentioned three-way handshake. This is the opposite of it. What does a connectionless mean? So what's a connectionless? What do you think? If I have process A sending to B using a UDP transfer protocol. So if I say connectionless, what do you think that is? You don't need to establish a connection to have sending an actual packets. So some sort of protocols like TCP, which will be the opposite, requires establishment, a preliminary connection, an initialization of the connection. Meanwhile, UDP don't have that. Basically, UDP is, if you want to send an application, just send it. If you want to send, a packet on a process, just send it with a synchronization number, whatever. That's it. No establishment of connection. You just send your packets, and that's it. That's how UDP operates. If I say connection-oriented is the opposite, let me explain it here. Even I'm going to let's explain it in TCP, just to show exactly the differences. But I'm not going to explain it in full details. For TCTV to create a connection, it needs something called a three-way handshake. In other words, you need to establish a connection between those 2 points to send the packets. For simplicity, A and B connected using 3 lines. Put it that way. If I'm using UDP, send information in any line you want to arrive to its destination. Nothing being controlled. Say that's UDP. If I say TCP instead, same example. A trying to connect to B. Same 3 lines between those 2 points. Because you need to have initialization, because you need to have a connection, you'll have a solid connection between A and B. You initiate, I'll explain the full initiation with the TCP, but you create that connection, and then you start using the connection to send the packets. Depending again whether you can use other lines, that's depending on the application at the end, but what I need to have that solid connection. For this one to terminate the connection, you just stop sending the packets. You don't need to terminate. In here, if you want to terminate the connection, you need to finish the connection. You need to stop that connection for you to stop sending, because it will create issues. Those 2 points, when I say it create issues, what do I mean? So if I say, I just don't send any packets, I don't finish it, what happens? What do you think happens? If you have a TCP connection, A and B connected, and you said, I'm not terminating it, but I'm just not sending anything. I don't care. What happens? What consequences will create? Can anyone know? What do you think? No? So what will create? You're using a line, you're using bandwidth, you are occupying that process, whatever that process. For example, you're using a port number inside an FTP transfer protocol without timing out. You'll still be using it until you say timeout, but that time is very long. Might be half an hour, whatever that is, depending on the application. Maybe there isn't. You just created now one, and you said, okay, guys, just use it, and you didn't put a timer there. That connection will be between those 2 points, used until I don't know when, until they turn off the machine or something happens. Okay, so you are occupying the bandwidth, you are occupying the connection, you are occupying the process itself. Okay. So no handshake between UDP sender and receiver. The handshake here is the initialization, is the actual setup of a connection. That I'm going to explain in full details with TCP because there isn't any in UDP. Each UDP segment is handled independently of the others. Okay? Because there is no connection. You can just send those segments in any way. When I say independently now, you can't go in any direction. In fact, it's going to go this way, or this way. You don't need to arrive in order. You don't care if it's missing. You just want to send them. That's basically what it is. Just send the packet. That's UDP. That's why speed is a very major point here. You can see how simple it is, and I'll show you the structure of it just in the next slide. That's how simple it is. It has a 32 bits of 2 type of 8 bytes of each section of those. If you look at it, it has the source port number and the destination port number. What's that? Source port number and destination port. What's that?
IP.
No, it's not. Port number is an address. But what are they standing for? From the name. It's the source and destination. It's an A and B. So if I'm sending a packet, this packet, if I would zoom in this packet, simply that packet will have this inside. A, source, B, destination. We'll deal with the address. It can be a port address because I'm dealing with what? With a process, with a transport layer process. The length can be the actual size of the actual data. So the question is this fixed? Is this being controlled by the application? What do you think? If I say this is a UDP packet, this is the actual packet. Does this should be the same size or can it be a different size? Why and who controls it? If I'm sending an actual packet, a data, using the transport layer, i.e. by an application, and that being divided into 3, 4 chunks of actual packets. Should they be identical in size or not? Why and who controls it?
And the application controls it.
And the application exactly controls that. So in other words, the application says this size of the packet can be, let's say, 2 bits, 3 bits, whatever, 4 bytes. Do they need to be the same size? Either yes or no?
No, it depends on the size of the packet. And send that same task.
Again, you said who controls it? You just said the application. So in other words, the application can decide whether you want to have an actual size of controlling the size of the packets or not. This is how flexible it is. So the length here will identify the actual size of the sending of the packet. If it's a 2 meg, sorry, if it's a 2 bytes, then it's a 2 byte. Let's stick with it. If it's up to 2 bytes, it can be 1 to 2. Put it that way. So the length will actually is the bytes of the UDP segment, including the header. Okay? Checksum. What's that? Error detection, thank you. We said this is unreliable. Why do I need checksum?
This is for the application to look at the packet or
I didn't understand. Why? So it's an unreliable service. We all agreed UDP is unreliable. But I have a checksum. Remind yourself, what does checksum mean? There's 2 parts of it. What does the CRC do? 2 things. One, so remember, if I have a reminder that there is what?
Reliability.
No? Don't remember. Don't worry about the R. Pretend to I've confused things now. Why do I need a checksum if it's not reliable?
to have confirmation that the packet arrived or something, to have an error message if you arrived or not.
So what you're telling me is if that was an answer, I'll give you like 8 out of 10. That's fine, because what he's telling me that yes, it is unreliable, but at least I need to tell the higher layer, look guys, there is an error. You deal with it. I don't care. So that's basically what it is. It's detecting, not recovering, not correcting. So there are 2 things. Remember, checksum means detecting an error and actually correcting it. So if I would say unreliable, you're just telling the lower layer or the higher layers, be careful, one of the packets just not arrived. I don't care, just go and find it. An issue, something happened. Okay, so that's basically what it is. I'm not going to go into details how internet checksum works, but I just want you to understand the principle, the concept, that in here, checksum means detecting the actual error towards the higher or the lower. You want to deliver a packet towards the higher layers, but at least you have what you're telling the higher layer, you're having an issue. Find it, solve it, ask for a redelivery, it's your decision. Okay? Is that clear? Why checksum now is in the actual UDP. Application data message is basically on the application message. So the application can have an optional part of adding more information. It can be even more size of the actual length of the data. So basically it's just an optional part in here. So let's really take a recap. First of all, UDP is often used with the streaming of the multimedia applications. I have a list showing you exactly all the applications that's available, and you tell me in the end whether it's a UDP or a TCP in your opinion. Basically, UDP is used for streaming. Doesn't mean that TCP is not used for streaming, because you still need some sort of condition control. I'll explain that. It's a loss tolerant. Rate sensitive, doesn't care about anything. The best efforts communication to arrive towards the destination. Other UDP uses, by other I mean kind of applications, DNS, SNMP. I'm not sure if you're familiar with DNS. Do you know what DNS is? What? Yeah, exactly. Domain name system. What is that? What does that do? Exactly. Humans understand. You don't remember what's the BBC IP address? No. What's the BBC website link? It's the BBC.co.uk. I'll try to make it easier, make it worse. So if you have any sort of it, if I say, okay, go and find an actual, that should be easier than that. Usually you know names rather than you remember numbers. So you can't say that, okay, BBC is 192.173.5.6. No one knows that. But it knows it's a bbc.com.co.uk. DMU.ac.uk. No one knows the actual IP address. So, okay, let's return to the UDP. What does UDP do here? Why would I need UDP here? Why would I need TCP? It's a very simple operation. Give me a name instead of the IP. So sometimes you write an address, you see the actual hypertext, try to translate it to a number, return it to a name, and show it to you. That's UDP operating. When an actual name is an actual given, that's basically using UDP. What else? SNMP. That's basically management network. That's an, I'm not sure exactly what's the acronym here, but it's for the management of the protocols within the network. Simple network management protocol, I think. Yeah. So basically uses UDP because it's a simple management of the actual network. So what I'm saying is UDP is for a light use, not for heavy usability. Although streaming is not light, but I need speed. Not every streaming operates within UDP, because typically we say UDP, but there is TCP as well. So I'm just trying to make a case that UDP is still used, even there's so many other services that are available within UDP. If I want to use a reliability within UDP, what do I do? What do I add? Like point to point, what do I add to provide reliable service? Sliding window protocol. Okay? Any questions before I go to TCP? Any questions? Okay, TCP. Transmission Control Protocol. Transmission Control Protocol, basically in the beginning, it was designed by the Department of Defense in the United States. If you look at the most of the more advanced technologies, it started basically from the DoD. It will be heavily tested for 3 to 2 years before it's been given to the other people in the public to use. At the moment, there are so many other maybe protocols, technologies that we don't know about. In 2 or 3 years, maybe we'll know about it. It's being tested. So who tested it first? Should be Department of Defense, wherever that is, whatever country that is. Mainly US are the leading department of that technologies. they have, of course, special access for people to go and see. I don't know what's there, but mainly most of those technologies. If I go back to ad hoc, if I go back to normal connections and packet switching, all of that's being done through DRIPR, and then it's done by DOT. There are departments, but mainly all of them is controlled by DOT. And TCP was one of those. Okay. The standard and most used protocol at the moment, Ethernet, that's CTC, provides reliability, variable length segments, byte stream. Single headed formats are in has flags to specify types and purposes of the segments, and how segment can be used, delivered, recovered, and flow control. Basically, TCP is what is the internet at the moment with the IP. Okay? So let's have a look now how complicated is TCP in comparison to the IP. And I want you to help me now with those fields. What's the source, port, and what's the destination? What are these in TCP? So similar to UDP. So what is those two stores? Basically your address. Your source and your destination. So the source port number, destination port number stands for your address, basically. What do you think your sequence number is? From the name, the packets. So why do you need it for? So to achieve that reliability. That wasn't available in your UTP because you don't care about the reliability. For you to have your sequence numbers, you need to have those to provide the reliable service. So sequence numbers. Acknowledgements. What else? Again, the same thing. If I would try to provide that reliable service, I need to have an acknowledgement from the receiver to understand that that packet has arrived towards a destination. Header length. What's that? Header length. We had a length there, which is similar to this one. In UDP, we had a length as well. What is it? It's basically your header file. So basically, whatever you have as a data and a header will be stored here. That's the size of the actual packet. And in here, within actual, with TCP, we have something called maximum size of the segments. So in here, the application as well will indicate to the user, to the destination, to the actual transport layer, telling him that you cannot send more than X amount of bytes for that segment. So in your application, can put that in detail, saying that don't send more than that. That will be stored eventually in the options, but will be indicated by the length of the actual size. Let's see, what's the window size? What's the window size? Actually, learn that from your slide window. Window size.
Amount of
exactly. So you need to control the actual number of packets being sent to as a destination because you need to control the flow of the actual network. Yes, that it is. Remember when we tried to make comparison? Now, if I go back to sliding window protocol, I need to understand what the sequence number is being used and why. I need to know why acknowledgement is being used, and then I need to know why do I need the max window size and maximum window size. So basically, that's it. That's available in your TCP packets. In here, we are indicating those numbers. TCP checksum basically is detecting and correcting errors. And again, I'm not going to go into details of how internet checksum operates, but as a principle, detects and corrects errors. The final thing I want to explain here is the flags. We have 8 flags available in the TCP. I'm going to explain each one of them in details. If I would look at the flags, at the moment I have something called acknowledgement. The RST, let's start with acknowledgements. Acknowledgement field, ACK. What do you think that is? We already have an acknowledgement, but we have an acknowledgement field. Why would I need that? What are you indicating here? If I say, by the way, flags are 1 and 0, basically that is, these are 1 bits. So if I put 1 or 0, what am I indicating in the acknowledgement? What do you think?
By the way.
Right or wrong, exactly. So you are telling him that acknowledgement had been arrived and I accepted. It's not that acknowledge a number, it's now I acknowledge receiving the packet. So if it's a 1, I acknowledge. If it's 0, I don't acknowledge. The synchronization, I think that they are together. RST, synchronization, and FIN, finish. All of those are together. What do you think these are? Those 3 flags. From the name, finish, restarting the connection, synchronizing. What do you think that these are? Wait, what are they related to? What do you think? Those 3 flags. Connecting, synchronization, restarting connection, finishing it. What do you think that is? What is related to what? Why do you need those 2?
Secure connection. Reliable connection.
Not reliable connection, just creating the connection. You remember we said that three-way handshake when we need something called connection-oriented now? TCP provides connection-oriented, i.e. it provides a 3-way handshake. Those 3 flags will indicate exactly how is that connection be happening. And explain exactly full details how a 3-way handshake is being done. But these are the flags that are actually controlling it as well. What we have left is something called URG, urgent data. This is basically telling the higher layers that this data is urgent. By the way, it's not being used. It's not being used, it's just there as an optional. It's never been used in any application because it's redundant. I don't know why they created it. It's still there. Okay? And we have something called push. It's the same as the urgent. Push the data to the higher layers. You don't need to tell me. I'm pushing it out. That's basically what it is doing. The process of an actual, from the receiving side, will receive and forward it to another process. The word push means just push it. Okay. This is the actual nature of an actual TCP connection. So again, it's been there, that's the duty, but it's not being used. Neither the urgent or the push are being used. I want you to understand exactly what that is. ECE and the actual CW are condition window reduced. That's basically the condition control, and I'll explain that within the condition part, okay? So basically flags are an indicator whether that action happened or not. It is 1 or 0, basically. Okay? Any questions before I move on with TCP? Is it clear how TCP is different than UDP at least? So there are things that are common. You need to have a source, you need to have a destination as an address, you have a checksum, whether each one of them has an individual working part, but at least they are doing the same, but they don't have a sequence number or acknowledgement, they don't have the flags, the window size, and other parts, okay? But they share some of the actual features within both of those protocols, okay? Any questions? Okay, before I go to the TCP connection management, let's take a break, 5 minutes. Come back, okay?
Too much to